video, we will be discussing about the subject VLSI design. Before that, let me introduce myself to you all. Myself Chandana, and I'm from Sri Venkateshwara College of Engineering, pursuing final year in Electronics and Communication domain. And we'll begin with a subject called VLSI design, which is very important for the electronic students who are willing to go to the core companies. The subject code of VLSI design is 18EC72, and in today's session we will be discussing about working of MOS transistor in different modes. We'll be seeing about the working of MOS transistor in different modes. MOS transistor. This is how MOS transistor will be uh, visible, and we'll see a MOS transistor typically it mainly consists of three terminals, namely gate, source, and drain. This is gate with one type of metal, that is P type of metal, and this is source, and this is drain. This is N P N type. The MOS transistor here which I have taken as example is NPN type, where it will be having three important terminals called source, gate, and drain. And this base will be P type substrate. Let's see the working of MOS transistor in accumulation, depletion, and inverse mode. We'll here discuss about three different modes, that is accumulation mode, depletion mode, and inverse mode. We'll see the working of MOS transistor here. This will be the semiconductor, and this will be the metal. E naught. The E naught which is mentioned here is defined as vacuum energy level, the minimum energy an electron must have to free itself from the material. The material refers to metal or semiconductor. So E naught will be vacuum energy level. That means the electron should have minimum energy, where that the electron should be free from the its substrate. That is the metal. Electron should have the energy of getting itself free from the metal or semiconductor. That is from the material. And phi m is work function. Here here phi m is mentioned, so that will be considered as work function of metal, and for semiconductor it is phi s, so that will be considered as a work function for semiconductors. So we'll take out all the markings in both, so that it will be easy for me to explain the next points. So I'll just remove the markings. Just a minute. Okay. Then phi naught, we know that it is the function of semiconductor. Let's see what does phi m deals with. Phi m is the energy difference from the Fermi energy of an electron in the metal to the vacuum level energy level, which means E naught, the difference between the firm energy and E naught, that is vacuum energy of an electron, which is also called as average energy. And uh, phi s will be work function of a semiconductor, as we saw, which is mentioned over here. And this energy is the difference from the Fermi energy of an electron in semiconductor to the vacuum energy. Both are same, but for phi m will be for metal, and phi s will be for semiconductor. And Here, X is mentioned in semiconductor. That will be electron affinity of the semiconductor. We know what is electron affinity, and this is the energy difference from the conductor, which is minimum in semiconductor to the vacuum energy level. Note that the energy does not depend on the doping materials. That is the energy of, or the energy affinity of semiconductor will be the difference of conductors, and also the minimum semiconductor of vacuum level. We have to note that this energy will not depend on the doping material. So doping material, it can be p type, or it can be n type, whereas I've shown it will be doped by n, p, n, or P, uh, PNP, or NPN, any type it can be. MOS transistor can be any type of doping. That is what X is defined as electronic affinity, and it should not depend on the type of dopings. And FB. FB is now given as phi S minus X in the quiescent neutral region, where the bands are not bent, or in flat band, that is the bands are not bent, or it is not flat. So that is given as FB. And that is for then here let's see for accumulation mode. For accumulation mode, the diagram is given over here. You can observe the diagram, and we are given here is average gain is greater than 0. Now let's see for n-type semiconductor. Here we are talking about n-type semiconductor, where when Vg is greater than 0, the metal Fermi energy is lower. So when average gain is low or greater than 0, the Fermi energy is low, and the insulator has an electric field across it that terminates almost immediately in the near perfectly conducting element. So it will terminate only in perfectly conducting element metal, and terminates over the infinite distance in semiconductor. So if it wants to um, terminate in semiconductor, then the resistivity or resistance should be infinite. The charge model indicates the negative charge must be created in semiconductor near the interface. So since n is equal to phi exponent of EF minus EI by K. So the electron concentration in semiconductor near the interface increases, and that is known as accumulation mode, where the electrons get accumulated near the semiconductor interface. Let's see about depletion mode, and this will be the diagram for depletion mode. In depletion mode, average voltage gain will be less than 0. So let's see, when Vg is less than 0, then the Fermi energy is raised, whereas in accumulation mode, when Vg will be greater, so Fermi energy will be lower, and in depletion mode, Vg will be lower, so Fermi energy will be higher. The insulator has electronic field across its terminators almost immediately in nearly same thing. Here electric field will be there across the terminates near perfectly conducting elements, and it terminates over infinite distance in same thing. It needs infinite resistivity to terminate in semiconductors, and it terminates in elements when it is perfectly conducting. So this will be known as depletion region. Let's go for inverse mode. Inverse mode will be having two things. One is holes, and one is ionized donors. So for n-type semiconductor, for higher magnetic bias, for n-type semiconductor higher magnetic bias, their voltage gain will be less than 0. And Fermi energy near the interface crosses intrinsic energy, and the type of material swaps from n-type to p-type. So here in inverse mode, we will be having both n-type and p-type at a time, and the swap will be taking place. Swapping of them will be taking place. So the Fermi energy near the interface, near the interface across the intrinsic energy will be more. And the charge model indicates that positive energy must be charged in semiconductor near interface, and this charge in the form of ionized donors or holes. It can be donors or holes. The charged ions can be holes or donors. And for n-time semiconductor, for higher magnitude of bias, the hole concentration increases, resulting in high concentration of holes near the interface, and this is called as inversion mode, which means the holes concentration increases only when the resulting concentration is very high, and that will be known as inverse mode. Thank you so much for watching my video. Don't forget to like, share, comment, and subscribe. Please press the bell icon so that you'll get the first notification when I upload my video. Thank you for watching today. Bye bye.